everyone. In this video we're going to talk about ways to display quantitative data. So we talked about some before, like a histogram and dot plot and things like that. So let's get right into this. So first we're going to start with drawing a stem and leaf plot. So a stem and leaf plot is just another way to represent quantitative data, and this is graphically or visually. And so in a stem and leaf plot, also called a stem plot, we use the digits that are anywhere from to the left of the rightmost digit to form what we call the stem, and then the rightmost digit forms the leaf. And so, for example, for the number 147, the rightmost digit is 7, so that's our leaf, and so the stem would be 14. Alright, so we're going to look at a table that represents the percentage of persons living in poverty by state in the year 2017. So here's that table, and notice the percent. It's always to the tens place here, so 16.9, 11.1, and so on for each of the states. So what we're going to do is form a stem and leaf plot using this data. So for example, for Alabama, 16 is the stem, and it was 16.9, so 9 is the leaf. Same thing, idea for Alaska, 11 is the stem, 1 is the leaf, and so on. And we do this for all of our values. If we go through all the data, we see that 7.7 was the lowest and 19.8 was the highest. And so our stem ranges are from 7 to 19. And then we're going to fill in our leaves after that. So we just organize from lowest to highest on our diagram. Now we're going to write the corresponding leaves. So we had a 7.7, we had a 9.6, a 9.5, and so on. And then what we want to do is rearrange the leaves in ascending order. So notice the digits now: 10.0, 10.3, 10.3 again, 10.5, and so on. So they're in ascending order in terms of the leaves. For 8 and 18, notice they don't have any leaf, so there was no values on our table for 8 point anything or 18 point anything, because if it was going to be like 8.0, it would have had a 0. Notice we have like 10.0 is 0. And so just the legend here, 7 and then our vertical line, -7 represents 7.7%. So the construction of a stem and leaf plot, we can break it into a few steps. Like we said, the stem is going to be the value the values that are left of the rightmost digit, and the rightmost digit is going to be our leaf. Then we write down the stems in a vertical column in increasing order, and then we draw a vertical line to the right. That's going to separate the leaves, and then we write each leaf corresponding to the stems. And then within those leaves that we wrote within each stem, we're going to just rearrange our leaves in ascending order. Okay, so an advantage of a stem and leaf diagram over histograms, which we've talked about before, once a frequency distribution or histogram of continuous data is created, the raw data is lost unless it's reported within the frequency distribution. However, the raw data can be retrieved from a stem and leaf plot. So basically, the advantage here is that you can go back and reference the raw data if you want to, if you have a stem and leaf plot. If you recall, with histograms of continuous data, we had intervals for our classes, and we just would say the frequency or how many of each class was observed. A split stem and leaf plot, okay, so the data in the table range from 11 to 48. The first figure shows a stem and leaf plot using the tens digit as the stem and the ones digit as the leaf. And the data appears rather bunched, okay? So notice we only go from 11 to 48, so the stems only go 1 to 4, and there's a lot of values for the leaves. So it's a little convoluted there. So what we can do to resolve this problem is to use split stems. So for example, rather than using one stem for the class 10 to 19, we could use two stems and just maybe cut it in half. So 10 to 14 for one interval, and then 15 to 19 for the other one. So you can see here, we sort of split it up so that it's not stretched out so much in terms of the leaves. And so notice, for example, 2, we go with the leaves for 2 from 0 to 4, and then the next set for 2 would have 5 through 9. Now let's look at constructing frequency polygons. So first, a class midpoint is just the sum of consecutive lower class limits divided by 2. So this is true for any midpoint. If you're trying to find the midpoint of 2 points, you add up the points and divide by 2. Now a frequency polygon is a graph that uses points, and then you're going to connect them with the line segments, and this is to represent the frequencies for the classes. The way it's constructed is by plotting a point above each class midpoint, which is on a horizontal axis, and this is going to be at the height equal to the frequency of the class. So what that part means is pretty much like if you think of a histogram or a bar graph, instead of drawing rectangles, we're just plotting a single point at what would have been like the height of the rectangle. And where you place that point is at the midpoint of the class, the middle of the class from the horizontal axis. And the next, line segments are drawn connecting the consecutive points. And then 2 additional line segments are drawn connecting each end of the graph with the horizontal axis. So let's put all that together so you can see it. So we're going to construct a frequency polygon of data that we've used in the past, in a different example, and we're going to calculate the class midpoints and then be able to construct this polygon. So from another video, we had information where our data ranged from, if you recall, actually, if you watched that video, it was 65 to 300 and I believe 21 or something. And so our class ranges were from 50, 75, and so on, class width of 25, and we had 11 classes. So what we want to do first is find the midpoint. So from 50 to 75, you add those up. Okay, so the sum of the two lower limits, notice we have that here, 50 plus 75, and then just divide that by 2. So the middle, or midpoint, of this class would be 62.5. Similar calculation, 75 plus the next lower class limit plus 100 divided by 2 would give us a midpoint of this class at 87.5. We can do that for each of the classes, and we would get each of these midpoints. That's where we're going to plot, at least horizontally, our point that is going to represent our frequency. And so the frequency of the data from within each of these classes for this range, this class, 50 to 74.99, was 1. If we jump down to 200 to 224.99, that had a frequency of 13, and then so on. Here we have the relative frequency. Remember, the relative frequency is the frequency divided by the total, okay? So in this case, the total was 50, so 13 divided by 50 was 0.26 or 26%. So here we have our frequency polygon. So let's just talk about how we draw this. Now you plot the points whose x-coordinates are the midpoints that you just calculated, and then the y-coordinates are the frequencies. And so let's just take one of these, for example. 62.5 was the midpoint of our first class, and the frequency of that class was 1. So we plot the point at the horizontal midpoint and with the height of that frequency. Let's jump to another one. The class, I think it was from 200 to 224.99. The midpoint was 212.5, and the frequency was 13. So that's where we plot that point. And then you connect the points with line segments. Now the new part, the interesting part, is these end line segments. So one going off to the end on the left, one going off to the end on the right. And basically that's the this sentence here, the midpoint of the class preceding the first one, and then the midpoint of the class following the last class. And the fastest way to do that is just to know our class width, which was 25. If you recall, the class went from 50, and then the next one started at 75, and so on. So we just take this lowest midpoint, and then if you just subtract the class width of 25, you'll get this next midpoint, which is 37.5. Very similar over here on the other end. Our last midpoint, if you just add the class width of 25, you're going to get this last midpoint. And then there was no values for those. That was outside of our data range. And so when your point is actually at a frequency of 0, and so your line segment is drawn down to the horizontal axis. The next thing we're going to talk about is cumulative frequency and relative frequency tables. So a cumulative frequency distribution is one that displays aggregate frequency of the category. Another way to say this for discrete data is that it displays the total number of observations less than or equal to the category. For continuous data, so different from discrete, for continuous data, it displays the total number of observations less than or equal to the upper class limit of a class. All right, so let's go through this. Real quick, let's talk about the cumulative relative frequency distribution. So it displays the proportion or percentage, just like our relative frequency did. So our table 17 displays cumulative frequency and cumulative relative frequency of the data summarized in a previous table. And so let's just go through this a little bit. We had some of this information already. We had the first 3 columns. We had our class ranges, okay? We had the frequency of occurrences in each class, and we can calculate from that the relative frequency. So those are things we've done before. Now the cumulative frequency over here in the next column is basically if you start like adding as you go. So the cumulative frequency in the first class, well, there was only 1 occurrence, so it's 1. But when we move to the next class, we count what we've previously counted. So even though there was no occurrences in the second class, we still had 1 occurrence or 1 frequency value previously. Then the next class had 7 for its frequency, so we just add that to the previous one. That's where 8 came from. So then next is 10 in the next class, so we say 10 plus the previous 8 is 18. And we do this for each class. We add the new frequency to the previous value, and then at the end you should always have the total number from your data set, okay, from your sample, because if you're adding up the frequencies, it should equal the total, which in our case was 50. And then the cumulative relative frequency, the idea is very similar to relative frequency, where you're going to do division, but you just divide the cumulative frequency by the total. So the first 2 was 1 out of 50, then 8 out of 50 is where 0.16 came from. Jumping down, 40 out of 50 is where 0.8 came from. And then 50 out of 50 is why we have 1 here. So this should always end with a 1, or in percent form, it should look like 100%. Next, let's talk about constructing frequency and relative frequency ogives. So an ogive is just a graph that represents the cumulative frequency or cumulative relative frequency for the class. And it's constructed by plotting points whose x coordinates are the upper class limits. So we're going to focus on the upper class limits, and then the y coordinates are the same. It's either the cumulative frequency or cumulative relative frequency. And then, like our frequency polygons, we're going to draw line segments to connect our points. We have an additional line segment. This one's going to be drawn down to the horizontal axis preceding our first class. So here's an example of an ogive. Construct a relative frequency ogive using our data from the previous table. and plotting points whose x-coordinates are the upper class limits, and the y-coordinates in this case are the cumulative relative frequency. So if you remember, our first class was from 50 to 74.99. So notice on our horizontal axis, we labeled 74.99. Our next class went from 75 to 99.99, and so we labeled the upper class limit. And we do this all the way across. And then remember our last class was from 300 to 324.99. And so our height of each point is the cumulative relative frequency in this case. And so it should look like it's going to go up because remember it has to reach 1 or 100% frequency if we're accumulating, okay, if we're adding them up. And so the extra piece is down here from our upper limit of our smallest class, our first class, we have to just draw one extra point, which would have been, you could say this would be the upper limit if there was a previous class. So remember, our first class started at 50, so we just go to the number right before that. In this case, it would have been 49.99. And that frequency is 0, so you draw the point at 0 and draw a line down. And then up here, like I said already, it's going to go to 1. So the last objective we're going to take a look at is drawing time series graphs. So if the value of a variable is measured at different points in time, then just because of that fact, the data is referred to as a time series data. So a time series plot is obtained by plotting the time in which a variable is measured, and this is going to be on our horizontal axis, and the corresponding value of the variable is on our vertical axis. And then we're going to use line segments to connect points. So in this example, we have what's called the Partisan Conflict Index, PCI. It tracks the degree of political disagreements among U.S. politicians in the federal government. It is found by measuring the frequency of newspaper articles reporting disagreements in a given month. Higher values of the index suggest greater conflict among political parties, Congress, and the president. Okay, so this data is stopping at 2018, so I'm sure it would be quite a bit different if it had years after that. So we're going to construct a time series plot of the data, and then in what year was the index the highest. So if we take this data, put our time on our horizontal axis, and then our height of our point is going to be at this PCI value. Okay, so here's our time series plot for our data. We have our years on the horizontal axis, and then our value, in this case for the PCI, on the vertical axis. We have a point at the intersection of the year and the PCI value. And then just notice a couple of jumps. In 2010 there was a small jump, and then in 2013 was the highest point. There was midterm elections this year, and then there was a federal government shutdown in the month of October this year, which is when this data was observed. All right, that's it for this one. Thanks for watching.